We're learning about polar and trigonometric forms of two-dimensional vectors. We've looked at vectors already in Cartesian form, or sometimes that's called rectangular form. So we might have a vector P which equals xi plus yj. We're familiar with that form. We're also familiar with a component form where we have one number then a second number, so that is component form. Sometimes we see that with things like storage vectors. But there are other forms, and we're going to look at two related forms that are quite different to the Cartesian form and the component or storage vector form. So we're going to look at polar form first. Polar form is basically denoted by an ordered pair, but it's not like that one, that component form. It's a different sort of ordered pair. The first number you see in red, that's denoted by P, is the magnitude of the vector, which if you drew it is the length of the vector. The second number gives the direction of the vector. So we're using a Cartesian plane. Now the convention, and you'll learn this in trigonometry as well, the convention is to make the zero angle here in the positive x direction and go anti-clockwise. Very important. Anti-clockwise is positive. So we start in the positive x direction and then we go around anti-clockwise and make an arc. That angle that you scribe is called theta, the direction of the vector. So for example, if we have 5, 30, that can be drawn as a vector geometrically with a magnitude of 5 and a direction of 30 degrees. The next form we're looking at is the trigonometric form, or sometimes just called trig form. And first thing we need to look at is a few little rules, little equations, which I'll explain. Let's have a look. If we look to the right of the screen, we see that for some generic vector v, in Cartesian form it would be expressed as xi plus yj, where x and y are scalars. Here we're told that x can be achieved by going r times cos theta, where r is that magnitude in polar form and theta is the direction, and y, we can yield y by going r sine theta. So if we sub those in, instead of x we've got r times cos theta, and instead of y we've got r times sine theta. So that full form v equals r cos theta I plus r sine theta j is the full trigonometric form of a vector. So where does that come from? Where do these two in particular come from? Well, if we look at drawing some vector r with a direction theta, we can see that it's basically going to form a right angled triangle. If we look at that zone there, if we isolate the triangle, let's bring it down there by itself, lower down on the screen, we've got theta and we've got r. Using your U9 trigonometry and putting in this distance y, which is some vertical distance, and x, some horizontal distance, if we start at the angle, cos theta is adjacent over hypotenuse, which should be x over r. So rearranging to get x by itself, we have to multiply by r, so multiplying both sides by r, we get r times cos theta, which is r cos theta. Same with sine theta. Starting at that angle theta, sine theta is opposite over hypotenuse, which would be y over r, and rearranging that one, y equals r times sine theta, which is what we have above. And while we're at it, let's look at how we get tan theta as y over x, which if you look closely is also y over x would be r sine theta over r cos theta. The r's would cancel out and you'd get sine theta over cos theta, which when in your future trig you'll discover that as well. That's not important right now, but it's an interesting result. How do we get tan theta equals y over x? Well, if we have a look, starting again at theta, tan is opposite over adjacent, which is y over x. So tan theta is y over x directly. The same result as last time. The magnitude of the vector is still x squared plus y squared, and I guess as a corollary of that, as a logical extension of that, you could call it r squared cos squared theta plus r squared sine squared theta, because that is x squared and y squared, but that there is not important right now, so that'll come later on. However, the things that are printed here are important, so please note the following that you see. Now for some examples. Example 1 below, change the following vector to component form. So we have a polar form vector there in the form r theta. We have to change it to component form, or you could change it to rectangular Cartesian form, either or. They both are the same essentially. So we basically, component form, or very similarly Cartesian form, is in the form of x, y, distance along the x and distance along the y in 2 dimensions. So we need to apply these up here. So basically we need to find x first. So x is r times cos theta, which would be 5 cos 30, which is 5 times root 3 on 2, which is approximately equal to 4.33 if you take a decimal approximation. Y is r sine theta, so that's 5 sine 30, 5 times a half, or 2.5. So in component form we have 4.33, 2.5. Or you could say 4.33i plus 2.5j.